Hello, good morning, everybody. Allow me just a second to check my sound and everything else. Excellent. All right, you guys in the chat say morning as well, so I suspect that the stream is working. I think we're online. Excellent. All right, good morning or good lunchtime or good afternoon or like wherever in the world you're sitting right now. Welcome to the first time ever I'm streaming anything online. I'll be honest with you, it's a little weird to talk to my computer and basically watch myself explaining things to me. We did a dry run on Twitch before, which was kind of funny, but I'm still not actually used to talk to a computer this odd. But I hope that this is all gonna work out just fine. Welcome to the first ever BlackHoodie virtual. 2020 has brought on many weird new things that we need to figure out, and for me, that meant to figure out how to do online classes. So here we are. What is BlackHoodie? BlackHoodie is a series of trainings that aims to bring low-level technological topics, very like challenging topics, to beginners. Usually our focus is to attract more women into the space of low-level hacking and security. And yeah, this mission continues. And the classes that we put on have the goal to be challenging. Like we're trying to bring like the topic of reverse engineering to people who've never reverse engineered before, just as an example, and try to start like at the very root of it, and throughout the training bring it up to a level where people can walk out and basically pick up a given binary and start working on it. The challenge there. In the email I sent people who signed up for this class, I explained that no one can learn reverse engineering within 8 hours. I'm very convinced of that. That's an estimation, but I've never seen anybody. 8 hours is a very short time to ramp up on this topic. The learning curve in the beginning is very steep. And yeah, that said, all that we tried to do with these classes is give people pointers and show you the topics that you need to study in order to get there, and give people a feel of how to work with the tools and how to get going. After this class, what you'll need to do in order to become efficient at reverse engineering is do your homework, do the things that I'm telling you to do, follow my advice. Apart from that, there is books and other tutorials out there, and the world is full of binaries, and you just need to pick one and get started, honestly. I keep telling my students that reading books is not going to teach you reverse engineering, which I experienced myself. I read papers and books for a long time before I actually opened the binary net debugger and started. And yeah, after all those books, I had an imagination of what to do, but that I wasn't actually, doing it. That said, reverse engineering is something very practical to learn. It's like programming in a sense. If you've never written an application, no book can tell you how to write an application, if that makes any sense. And with reverse engineering, it's the same thing. All right. Anyhow, I'm barely waking up. It's 8 o'clock in the morning in Portland, and I have really no idea why I scheduled this so early. But I'm prepared here with my coffee. I hope you guys are all ready to go. And just give me a second. By the way, behind me is my hilariously chaotic kitchen. 2020 also kicked me out of the office I usually work in, and this is the environment we have to deal with today. Anyhow, first things first, I will need you to download the class materials. Therefore, I'm asking you, where's my C? Navigate to the BlackHoodie GitHub, which can be seen here. The address is this one, github.com/blackhoodie_virtual, blackhoodie_virtual. This is where you find the class materials. This link was also in the email I sent to people who signed up for this class. You can simply click on it. You can get those materials by checking out the GitHub or by downloading it from the site. I said it's like the first human ever on GitHub. Yeah, GitHub and me have a funny history. I've been using GitHub for like a decade and I still don't know how to use it. But an important thing, I updated especially the exercise binaries that are on this repo 3 days ago. It's not true, 2 days ago on Saturday. So if on Friday people already went ahead and downloaded the materials, please, please, please update the binaries. I recompiled them and they look slightly different than the older version. And it is important that we all look at the same version of those binaries, just so that we don't get lost in the disassembler. All right, so please go ahead and download the stuff, and you can also find the slide deck on there that I'll be using today, which is very, very sparse and short and not very detailed at all. And you will find a file called links_reading material in there. In there, I collected all the links that I also added in the presentation. So throughout the presentation, you'll see some topics have a link in the bottom where you can find more information about a specific topic. And that's important if you want to study up on a specific topic after class. What's also in there, let me have a quick look. I think I added it, yeah. I also added 2 books down here. Oops. Here. And we won't be reading books in class. And I already ranted about books. These 2 are specifically good to either study the introductory stage or like study topics that you need to understand in order to be able to understand the binary. I like to recommend especially the first one for beginners. It's called Reversing Secrets of Reverse Engineering. It's rather old and it's based on 32-bit, but the first couple chapters in this book very nicely line up all the topics that need to be understood in order to get going, like operating system internals, like what's an API, like what's a file format, which tools do we use, how does a disassembler work, how does a debugger work, all of these topics in great detail. We won't be looking into all of these topics in this class, like the time is just too short. I'd rather we do a couple more exercises and a little less theory, because the theory you can go and read up on by yourself. Like you don't need me to explain to you how exactly a file format looks like. However, the step from understanding how a disassembler functions to understanding how to read disassembly, that's a little more tricky, which is why in this class, you and me are going to go through a lot of code and a lot of assembly, and we're going to read it together. And trust me, that sounds easier than it actually is. About the level of the class. So If you have prior experience in reverse engineering, this class is very introductory in the sense we're starting from the first hello world that's 3 instructions long and work our way from there to a legitimate Windows DLL. I'm not saying this is not the training for you, but if you have reverse engineered Windows binaries before, this might get a little boring. On the other hand, if your experience is rather high level, or if you have looked at a couple CTF examples before, but haven't actually reverse engineered into a real application, I might still be able to tell you something here. So yeah, stay tuned. All right. By now, I hope you guys got your binaries. And here is my incredibly pretty presentation. Yeah, I guess this is as good as it gets. I found out this weekend that you can't start a PowerPoint presentation that takes the full screen while still looking at other tools on the machine. Yeah, it's 2020 and we keep learning new stuff. Beautiful. All right, again, welcome to this class, to the Introduction to x86-64 Reverse Engineering. First, to the question, what is assembly? Let me just see for a minute whether I can change the zoom in here. Oh la la. Yes, I can. Beautiful. All right, first to the question, what is assembly? That seems like a very simple question, but could be answered in a book. Assembly is what your computer understands from the programs you feed it. Where to begin? For most people, when they think of assembly, they think about the textual representation of machine instructions. So if you look at the disassembler output, you see push and pop and add and move and soar and these instructions. And in reality, this is not what the CPU consumes. So if you look at the disassembly, this is something that is parsed in order for human to be able to read it. I say this very skeptical because this is exactly what we're trying to learn here, and this is what lots of people think is black magic. By the way, reverse engineering is not some mystical, magical unicorn capability. It's difficult and it requires a lot of time and training to learn, but it's not rocket science. So people try to sell you the idea that reverse engineering is something that's impossible to learn. It is not, I swear. Back to the assembly. We'll see later on when we look at the hex editor, the different forms of representing, it's called bytecode. What happens is that you have an application, a human-written application. You see the source code. The source code is consumed by a compiler. You might have heard about that. The compiler spits out bytecode. There's many different components involved there. From the compilers and linkers. I have to watch out not to talk too much about that. So in the recent years, I worked a lot on compiler internals. and that's why I love compilers so much. But in reality, simplified, what they do is they consume source code and spit out bytecode. Bytecode, on the other hand, is ineligible for the human being. I say this like there's never been anyone who's able to read bytecode, but yeah, it is just very hard. The bytecode representation is something which eventually is consumed by the CPU. We as human beings, if we want to reverse engineer a binary, we need tools to represent bytecode in a human readable form, which is called a disassembler. So a disassembler goes on to parse the bytecode and interpret it in into opcodes or into mnemonics that people can read. All right, now I've talked enough about this very simple question. Something that's on this slide, which I really want you to embrace, is the x86-64 cheat sheet from the Brown University that I found on Google. It's a rather nice, like a concise, short cheat sheet, which also explains lots of things that we'll discuss in class. Excellent. You're tasked to look through this cheat sheet as a homework. Then, the first thing we're going to do this morning is look at our first example, which is Hello World. Therefore, I will ask you, on the GitHub, there is a file which is called virtualbh.c. This is a very short and rather really useless piece of C code, which we will use as an exercise sheet. And now, as a first exercise, I'll ask you, open up the C file and copy the first function that you see in there. Like grab what's dubbed exercise 1. That is a hello world. Yeah. Many of you are probably experienced programmers, much more experienced than me, and your last hello world has probably been decades ago. Yeah, welcome back to the beginning. So please grab that piece of code and navigate to a website called godbolt.org. That website is also listed in the links text file on the GitHub. Godbolt.org is a very, very cool website. It's called the Compiler Explorer. With the Compiler Explorer, technically what people do is check how code looks under different compiler conditions. Like you can see how different compilers interpret source code and how different optimizations might play out on a piece of code you've written and how different optimization settings affect your code. Now, when I navigate to that site, I see a little function that's already in there. It's just an example which says int square, return num multiplied to num. We're not going to dive into this now. But something you can see immediately is that the different lines of code, like if I have this one line that says return num times num, the yellow color on the left and the yellow color on the right means it's the same input plus output. So here we can see that this one return line results in these two instructions that are visible in the output assembly. Anyhow, we're going to dive into this in a little bit. Now, please go ahead and dump the hello world in there. Yeah, I should copy paste that too, I suppose. copy, paste. Ah, shoot. Okay, don't only copy the hello world, but also bring the imports. Told you, programming is not my favorite hobby. All right. So this is how the screen should look like after we properly copied everything that we needed. You can see the first two lines are the imports that I had in the original C file. And then you have to void print hello and printf hello world. All right, let's get to the exciting part. On the right side, you can see the disassembly as produced by the x86-64 GCC compiler. In that case, we see the beautiful assembly annotation that GCC produces. On top of the screen, you will see a constant like the hello world string that we defined in the printf, like this one in here, will be located in something called the data section in the output binary eventually. Here this can be seen with this annotation .lc0. Do not ask me about the naming conventions about the GNU assembler. Why in the world that would be called LC0? I'm sure there's documentation about it somewhere. Anyhow, but it's just important that there is a constant string which will be identified by this placeholder called .lc0. From there, let's have a closer look at the assembly. You will notice that there is a call in here to a function called put_s, which stands for put string. There should be a call to printf here, but the compiler decided that put string is the better option in this case. So it optimized away the printf and put the put string there. That's compiler internal decision, which I will not explain right now. No, I will. Technically, what happened is we have a constant string here, and printf is, would usually expect more than one argument. So it would expect the string and possibly variables or strings that it could replace in the string, like a format string. And it is slow, like printf is very, very exhausting for the CPU as compared to the put string function. So the compiler thought, since we do not have any replacements in the string and really just want to put out a constant, we'd rather use the faster version. Yeah, you see I'm a little compiler nerd. What is really interesting for us here right now is these two lines. As you might have figured, the printf line on the left results into a move and a call instruction. Now, what is the other stuff? Yeah, you see, we could talk for hours about this hello world. What we're going to learn in this class is why we have this prologue before the two instructions of interest, why we have this epilogue after the two instructions of interest. Then, within the two instructions of interest, why is it two instructions and why is there a move to one particular register? All the questions I've just asked particularly have to do with how the function stack frame is set up and torn down. And we'll be talking about function stack frames quite a lot. And the second question of like why we load our string offset into a register here has to do with how the put string function receives argument. That's called a calling convention. That is the other big topic that we're going to discuss today. All right. Look at this code for another second. If you can deduct that LC here identifies our string and the call instruction calls put string which will output our string on the screen. Then you just successfully reverse engineered your first binary. Congratulations. All right. But where do we go from here? You can imagine binaries get a little more complicated in Hello World. And this is what we're going to be looking at now. First of all, let me just quickly get back to the bytecode. What you do not see in the compiler explorer is that this is not what the compiler puts out. Okay, so we feed this hello world to a compiler, and what the compiler eventually produces is called bytecode. Let me quickly show you what that means. All right. So I just changed the focus on Twitch, and now we see HXD. If you want to follow along here, please go ahead and open the HXD application that I mentioned in the prep we will need in this class. Otherwise, you can just follow my screen because this will be very quick. What I want you to see in HXD is bytecode, the mystical, magical bytecode that I keep talking about. So I'll open the virtualbh.exe application in HXD, and the HXD shows me the insides of the file. In classes that I've been teaching in the past, I had a lot of students go, whoa, when they first saw the hex editor, because, yeah, again, it's not rocket science, it's how the binary looks like on disk, but I still actually, I love to look at hex dumps. Anyhow, yeah, what we're looking at here is the, so to say, intestines of our executable. And if I scroll down a bit at offset 400, we see what's called bytecode. This that I'm marking here, that is executable bytecode. And a lot of it. How do I know this? That is a different question we're going to talk about when we speak about file formats. Anyhow, let's stick with the instruction pipeline for a second. So this here is bytecode. Bytecode is consumed by the CPU. I mentioned it before. I'll navigate back to the slide. So now whenever I talk about bytecode, you people think about bytes and hex values. Okay, so for the CPU consumes those values and decodes them into instructions and, yeah, prepares the different components that are inside of the CPU and then feeds those instructions to the internal pipelines. That is a very lengthy and very fascinating process. I work for a chip manufacturer and can tell you there's some 50 years of development went into CPU internals, and they're really just utterly fascinating. It is really, really complicated what modern CPUs do with instructions. If you're interested in that topic, and I really recommend you to be interested in that topic, please follow the link that I posted on this slide, which is also in our text file, and read up more about what exactly instructions do inside of the CPU. Yeah. For us here today, it's just important to understand that there is the bytecode, which goes into the CPU, and then magic fairies produce results, and one instruction after another change the state of the CPU. By changing the state of the CPU, we advance the program state and actually execute the bytecode that makes up our executables. Beautiful. Next slide. Program counter bytecode assembly. And sorry, what? Now that I've talked about bytecodes in a very lengthy fashion, let's talk about all the other things that are involved. For us as reverse engineers, CPU internals aren't all that important. What we need to understand, though, is certain components of the CPU that help us reverse engineer, or like that are in use by the application while executing. On this slide, you can see a very beautiful screenshot of IDA Pro while debugging. So this slide shows you the debugger view of IDA Pro, which is why everything's kind of mint green. God knows why they used mint green backgrounds. And what I wanted to show you here is the different components that are important to us. As a reverse engineer, our main focus is on the bytecode in the middle. So you see here, this is actually the exercise binary, an old version of it. Anyhow, so what you would start looking at is this little corner in the middle of the screen. But the rest is important too. Where to start? On the left side here, you can see again the infamous bytecode that I've been talking about for so long. And you can see the relation. So this stash of bytes, like 48, 83, EC, 28, etc., that's the bytecode that makes up the assembly. The disassembler went ahead and looked at those bytes. That's the executable code, and interpreted it into disassembly. So then on the right side of this little fraction of the window, you see a sub instruction, you see a call instruction, another call, a move instruction, and so on and so forth. This is what the disassembler did. This is not how the file originally looks like. This is important to understand because disassemblers can fail. Dum, dum, dum. Something that as a reverse engineer is important to understand, that the tools at hand, the tools that we have, they do their best to produce readable, comprehensible, and complete and correct disassembly output. Sometimes they can't. Disassembling modern binaries is something very complicated, and the tools that we have nowadays, some are better than others. Most of them produce nice and readable and complete disassembly, but sometimes it's not the case. And as a reverse engineer, it's important to understand, is this disassembly something that represents correctly what the binary is doing? Or is stuff missing? Or is stuff disassembled incorrectly? This is especially important if you plan to work on malicious binaries who often try to hide their intentions and to, well, obfuscate the code. And yeah, having worked on malware for a long time, distorting disassemblers is the ugliest thing malware authors can do. Like, if our own tools start lying to us analysts, we have a lot of work ahead of us. So that's really nasty. Anyway, in this class today, we're not going to look at anti-disassembly measures. That'd be cruel. What else can we see here? On the very left side of the screen, you can see addresses. These long numbers where it says 000-7FF65B711A0 and A4 and A9. Those are 64-bit binary addresses, and these show where in the virtual address space our program is mapped, or where our code is currently located. We're going to be talking a bit about what virtual memory is a little later and why that matters to us as reverse engineers. Then, the other important thing on the screen, by the way, we're going to be looking at IDA Pro in a bit. I planned to use Ghidra in this class, but honestly, I didn't have the time to wrap my head around Ghidra. I never actually practically worked with Ghidra. I like the idea of working with it, but I haven't gotten there yet. But we're gonna have a look at it anyway, just so you see different tools and how they interpret our binaries. Something that I like about IDA Pro a lot, I know it's a commercial tool and I know it's hilariously expensive if you want the full version, but what IDA Pro does is, or like what IDA Pro does really good is interpretation and presentation in a way that makes it easy for analysts to find the important bits of the binary. You're going to see in a bit what I mean by that when we look at both tools in comparison. And yeah, the reason why I used an IDA screenshot on this slide is, again, because it so prettily presents all the things that are important. Again, in the center, we have the IDA view, it's called, which presents the assembly. On the right side, we see the general registers. Registers are, well, technically, they're a piece of memory in the CPU that is very, very fast to access. On 64-bit, we have 16 general purpose registers. In reality, the CPU has thousands and thousands, or like the CPU knows thousands and thousands of registers. If you're interested in what that means or what I'm talking about here, please open the Intel manual and the chapter where it talks about MSR, model-specific registers. You'll be amazed of how many registers there can be. For us, also interesting, on the very, very right side of the screenshot is the status register. The status register is one register which identifies a number of bits. So each line in here, the CF and the PF and the AF and the CF and the SF and all these, those are individual bits in the status register. These bits, as you can guess, show the status of the CPU as the application executes. Like, for example, the CF stands for zero flag, and the zero flag is set if an instruction delivers a result of 0. Surprise, surprise. Now, yeah, we're going to be looking at those flags in a little bit as well. Sounds a lot simpler than reality, than it is in reality, to be honest. Anyhow, let's go clockwise. The next thing that's important. Here in the bottom, you see the stack view. Like I said, the registers are technically a piece of memory that's very fast and easy to access for the CPU. The stack is another dedicated piece of memory that the CPU uses that's a little slower. When I talk about fast and slow, we're talking about time units that are incomprehensible for human beings, like millimicro something something nanoseconds versus millimicroseconds that are not nano. I have no idea about those time units actually, but we're talking very, very, very fast versus very, very fast. Okay. The stack is something we're going to be talking about a lot. And as you can see here in this representation, it is like individual values stacked on top of each other. Yeah, it's a stack. So introduction to computer science, data structures, stacks are LIFO buffers where you stack one value, then you stack another value, then you stack another value, and you keep going. And once you're done with stacking, you can pop the values off again. You can stack new ones, and then you pop again. Yeah, this is technically how a stack works. And stacks are very important for us because the stack holds technically what a function uses as it executes in terms of local variables and arguments. Yeah, we're going to be talking about that in a bit. And on the bottom left, you can see the Hex View. IDA has this Hex View, which I love, 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 because you can synchronize it with registers. So this in the screenshot, the Hex View you see in the bottom is synchronized with the instruction pointer. The instruction pointer is also called program counter. It's also called RIP, sometimes called EIP, sometimes called PC. There's many different names, and that's sometimes slightly confusing. What it does is it points to the next instruction to be executed. That's very, very important. The instruction pointer is the one most important register in our stack of registers. You can see it on the right here. It's called RIP in this screenshot anyway. And you can also see that the address it holds, like RIP here, is the same address that you see in the IDA view on the left side. So here in this beautiful maroon purple color, this number, this 64-bit address, is the same as is placed in the RIP register on the right side. Now, imagine this is a debugger, and imagine advancing the debugger, which I would usually do with the key F7. Then this maroon line would jump onto the next instruction, the sub-instruction would be executed, and the instruction pointer would be advancing to the next instruction. That would be here, 711A4, etc., etc. So the instruction pointer, its job is really just to point to the actual instruction that's just been executed. Good. Where was I? The hex view. The hex view in this case is also synchronized with RIP. And here, if you check like the 48A3EC28 is exactly what we see up here. So these are the same instructions that are about to be executed in bytecode form. Why am I so excited about the hex view? We could go ahead. I mean, I can't because this is a screenshot, but in IDA you could go ahead and synchronize this view with another given register. So in our case, say we're interested where RDX is pointing to, because here RDX holds something that looks kind of like an address. We could synchronize the hex view with RDX, and you'll see later on why this is something that we might be interested in if our application processes data that's pointed to by a register. We can watch in the hex view how this data is modified. Not this week, but maybe next week, we will actually manage to debug an application. And I'm thinking maybe I find some self-modifying code so we can actually go ahead and watch a program modify itself. It's also very cool to see. All right, but this is it for this slide. Now, we'll be looking at each and every of these different components in more detail. Next slide. This is a very, very nice graphic that I include in all reverse engineering introductions I've ever taught because it's just so cool. And it shows us how a disassembler thinks. This slide, this graphic represents 32-bit instructions. So it is hilariously outdated. And if you use this table and go ahead and try to disassemble a modern day program, you will probably not be very happy. Anyhow, for us to understand, is a disassembler, all it does is it takes one byte after another. And this is an understatement. Disassemblers are very complex nowadays as well, and there's different methods about how to go about disassembling code. But essentially what it does is it takes a bytecode, looks up in the table which instruction the bytecode could be. And if you see here, if you look on the left side with me for a bit, if you see like the first byte is a 2 and the second byte is a 1, we land in this AND box here. So the disassembler knows that the instruction we're looking at is an AND instruction, And from the following bytes can determine what exactly is handed over to the end instruction. Like what are the operands that this instruction is working on. And from there it determines like how many bytes are being occupied by this one instruction. Then it parses the instruction into text representation and goes on to the next byte in the chain. Something important about the Intel architecture is that we're looking at different length instructions. Just a quick look here at the byte stash that we disassembled. So the disassembler went on, looked at 4 and 8 and found out sub instruction, then looked at 8 and 3 and E and C and to 8 and figured out this is like the stack pointer that's subtracted by 28 bytes. Okay, this instruction is 4 bytes long. If you look at the call instruction, if we call a 64-bit address, we're looking at a 5-byte instruction. Yeah, there's a E8 270000. That's 5 bytes. If we look at a XOR instruction, down here is XOR EAX. That's 2 bytes long. Now, disassembler knows that. Disassembler realizes like we're looking at a XOR instruction, and in this case, we need to parse 2 bytes, and after we parse those 2 bytes, we go on to the next hash. That is a little complicated, which is why sometimes disassembler fail. Imagine, especially if we have like anti-disassembly measures, imagine the disassembler thinks that this move instruction here is only 4 bytes long for whichever reason and starts parsing at the 5th byte, here the 00, then the instruction that is displayed after is wrong. And effectively, quite a number of instructions that the disassembler parses after this one faulty instruction is wrong. So the assembly that we see in the disassembler might be broken. For us as analysts, that would mean that we need to tell the disassembler what to do, which is why we need to understand how disassemblers work. This much about that. Yeah, and this graphic is just, it's awesome. It's colorful and all the rainbow colors. There's like more details in the bottom. And yeah, I really recommend you spend some time on staring at this and try to understand how instructions are made up. For us, more theory, beautiful. What is an instruction? Like, if you look at the disassembly of a binary, how can you understand what a specific instruction wants to do? Turns out there's documentation, which is great. Every instruction comes with a manual. The official manual is the Intel Software Developers Manual, the SDM, which is also 4,000 pages long, like a little more than 4,000 actually. And in there, you find a little chapter for every instruction that exists on an Intel system. If you ever have a look in there, you'll realize this is a lot of instructions. And lots of people think that we need to understand all of those instructions in order to be able to read assembly. I'm telling you that's not the case. Most of my reverse engineering experience was 32-bit Windows applications. 32-bit has been a while ago, I know. Now we're like on 64-bit for more than a decade, and 64-bit in reality does show a higher variety of instructions. But in the introduction, and I don't want to make it look too easy, but if you get started in reverse engineering, it is really enough to understand a handful of instructions. Like 90% of instructions you will see in a regular binary come out of a pool of 20 to 30 instructions. If you look at that, pool, like you're about to learn a language, like you're trying to learn French, you need to learn hundreds, if not thousands, of vocabularies. And after you learn those vocabularies, you need to understand how to put them in context with each other, like to put them into phrases and how to form sentences. And yeah, that's a lot of work. But for some reason, people aren't scared at all of learning French or Spanish or English for that matter. And I think that's because languages seem so much more natural to us. Like for reading a newspaper, you need to understand how to read the text that's printed in there. For reading a binary, you need to understand the text that's printed in there. Like you need to understand your vocabularies and the couple of rules um, that are required in order for those vocabularies to fit into phrases. And what I'm telling you now is like we don't need many more than 30 words, like 30 vocabularies, in order to get started. With 30 vocabularies in French, I don't think you can start a conversation with anyone. Anyhow, never tried that either. If you want to understand the French vocabulary, you look it up in the dictionary. If you want to understand an Intel instruction, you Google it. You could open the SDM, but what I recommend, what I usually do, is you type in the instruction and in your preferred search engine, and you look up a website that shows you the documentation. Why I say website is because the SDM is very unwieldy. It's very hard to navigate because it's just so many pages. And Google is often quicker in finding an explanation. So yeah, what I did here is I went to a website called felixcloutier.com, and I've never met Felix or know whoever he is, but he put up pretty much the whole Intel manual, or pretty much every instruction documentation that there is onto his website. So now if we look for the INC x86 instruction, we find this page, which pretty much shows us the same thing as the SDM. If I look at this and I look here, the SDM is a little prettier, but it's the same information. What does it show us? As analysts, what's the most interesting, I guess, is this tiny little corner thing down here. It's called operation. And there you see that the destination receives the destination plus 1, which is exactly what INC does. INC receives one operand, and this one operand will be incremented by 1. It's a super simple instruction. There is a description which explains of how the instruction operates, what it receives, what it can operate on, and what it does with it. And this box up here is highlighted because it shows us what the instruction can perform. So in this instruction field column here, you see that we can operate INC on a register or a memory operand. And the memory operand can be either 8 bits, 16 bits, 30 bits, or 64 bits. So this is how you would read this this manual. The STM, like, originally has been written for operating system designers, people who need to write software that runs on the CPU core, which is not what we're doing. So there's a little too much detail in here for us as reverse engineer. But again, the one most important part, if you look up instruction documentation, is this operation bit that's down here and marked with an arrow. This is where we find out what the instruction exactly does if we want to understand it. Great. Now we'll get started with the actual stuff. At this point, I have to say talking to my computer hasn't been all that weird, but what's a little strange is that I don't actually see your faces. And usually I derive from the looks that people have on their face of how much explanation I need to add to a certain bit. Like if I'm talking about the stack and how values are stacked on there and people look at me like with these big eyes and be like, what is she talking about? Then I explain a little more, and right here I don't quite know. one thing. Yeah, Granlis just mentioned that in the chat. Please, if you have questions, ask them. Something important throughout the class, and when we look at binaries, sometimes I will throw questions at you. Like, we're looking at 3 instructions, and I will tell you, what does this mean? Like, what do you think is happening here? In such cases, when I ask questions, it's not because I need your answer. It's not because I need you to run to the chat and tell us and everybody like what you think is there or what you understand there. That's a little harsh to say. Like, if we were in a room together, I would tell you, everybody think about that question and everybody think about an answer. And after everybody thought about it, someone can tell us the answer. Like, someone can speak up and tell the answer. What often happens in classes is, like, if your instructor asks you a question and there's always 1 or 2 people who know every answer immediately because they're geniuses. And those people usually are like, oh yeah, I know the answer, and the answer is na na. And then other people do not think. What is important though, when I ask you a question, I want you to think, right? I want everybody to come up with their own answer. And then we can talk about the explanation. So yeah, I really don't need you to explain the thing to me, but I need you to explain the thing to yourself. Right. I see the chat is moving. That's good. Are there any questions so far that we should be talking about? That's quick. How do shellcode injections work and how does it look in bytes? Where do you want to inject your shellcode to is the first question. So like, shellcode is just executable code. We might be looking at that a little bit later too. Shellcode, like if you remember the bytecode that I showed you in HXD before, that is executable bytecode inside of a binary. The binary header and the executable file format around it is just cosmetics. If you take that bytecode and insert it into a running program and manage to direct the instruction pointer to that piece of code, it will execute the code nonetheless. Good. What else do we have? Is it legal to reverse normal software? That depends on the license agreement that comes with it. The general rule is that on Windows, software is likely to come with a license agreement that does not allow you to reverse engineer it. So it's generally safe to assume that you're not allowed to reverse engineer Microsoft Word. On Unix systems, lots, like most software, as far as I know, comes with, like, for example, GPL or other Unix licenses, like open software licenses, that typically do not come with that clause. But yeah, watch out. It is a tricky field. Do not reverse engineer stuff that you're not allowed to reverse engineer. And again, the detail about this is usually hidden in the software license. Can you explain more what flags do? Yes, we'll be talking about flags in a minute. Whether the legal situation depends on the country. In reality, it doesn't. Like, the license agreement determines what you're allowed to do and what not. The question with the country is whether it's prosecuted in a certain country, or like whether someone actually cares as they're sent. But I wouldn't work with the assumption that it is it is okay just because no one follows up on it. Um, yeah. If you're interested in the legal situation, there's been a couple very high-profile cases in the past of people like publishing exploits on something they were not supposed to reverse engineer, and you can get into trouble doing so. We'll be posting the reversing lab setup. The lab setup is very easy. I do not plan to upload a virtual machine, but the lab setup that we're talking about is installing 4 tools on a Windows host machine. The instructions for that are in the email that I sent out or in the announce actually. So we don't technically have a very sophisticated lab. You need to install the community edition of IDA Pro, and if you want to install the HXT hex editor and CFF Explorer, which is the tool we're going to use. And that is it. Yeah. Our exercise binaries are not dangerous, so you don't technically need a virtual machine. If you're more comfortable reverse engineering in a virtual machine, then get yourself a Windows VM and set up the tools in there. That is all we need today. If you plan to professionally dive into reverse engineering over time, you will want your own lab setup, but how that looks like depends on what exactly you want to do. What my professional setup looks like. So, I work at a chip manufacturer. I don't have a reverse engineering lab myself. I have IDA Pro, which is pretty much all that I'm using nowadays for work. Back in the day when I was working as a malware reverse engineer, the lab setup looked wildly different. Like, you do not want to reverse engineer malware on your host system. You want a virtual machine, and there's like different tools like for sandboxing or for dynamic analysis, or like tools like Wireshark for observing like a thing while it executes and so on and so forth. There's very good material on that on the internet as well, if you're interested in how to set up such a malware analysis environment. But yeah, for reverse engineering, like for the level of reverse engineering that I do nowadays, IDA Pro is good enough. Pre-built Windows VM, yeah, it's all good. Excellent. A little bit of an overkill on lab setup, as Synaptic Rewrite says. Yeah, you can go wild on your analysis lab, and there's so many tools out there. And someone says either free now supports x64 debugging. Are you real? It might. That'd be so good. I cannot speak to what ARM processors will do with Intel. All right. Super real. Okay. Yeah, I'm excited about that. Honestly, the reason why I thought that Ghidra would be a good option to try out was because I thought they came with a debugger. When I saw though that they have a stub, like there's a plugin which allows you to attach GDB or something, I was less excited because that seems tedious. But yeah, I should see IDA Pro has this little debugger field. Excellent. So debugging will be something we do next week. And then you see this beautiful, beautiful mint green screen of the IDA Pro debugger as well. Awesome. Someone says Ghidra is amazing and has good documentation. Yeah, I don't doubt that. Ghidra is awesome. The fact that it was published and I hear the scripting interface is very cool. Like automation is something very important in reverse engineering, and the tools, like the automation options in disassembly is not amazing. All right, Ladies and gentlemen, we need to move on. Last question. Is there a reason to reverse engineer on Windows over Mac? I started out on Windows as a Windows malware reverse engineer. That's why I'm a Windows person, but you don't really have to stick to that. A tip for the beginning is if you just get started, stick to one operating system, stick to one file format, stick to one processor architecture. Like if you find out OS X is the way for you to go, then start there and stick there and reverse engineer binaries that run on there. Simple reason is like there is not big difference. Like if you reverse engineer Windows applications over Linux applications, you're looking at a different file format and you're looking at a different API. But if it's all 64-bit Intel architecture, it's rather similar, and the step isn't that big. But for a beginner, it can be very confusing to look at those little differences and say like, why I don't understand these instructions over here and these instructions over there. So yeah, stick to one platform until you know what you're doing, and then branch out to different platforms and file systems, file formats, and yeah, and so on and so forth. Excellent. Thank you for all the questions. It's great. There's people listening. It's awesome. Okay, let's move on. Registers, memory, and instructions. That's the three big topics that we need to wrap our head around before we dive into the disassembler. General purpose registers. Very, very important, and something I talked about swiftly before. A little bit of history class here. The registers we'll be working with are called general purpose registers. That's because they can be purposed for different tasks. That's a rather dumb explanation, but you'll see what I mean in a second. So on 32 bits, we used to have 8 general purpose registers. Those were EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. The E stands for extended, because you might recall that before the 32-bit processors, there were 16-bit processors. On 16-bit processors, the registers were called AX, BX, CX, DX, etc., etc. So the E really just means that we're on 32 bits now. And you'll see in a second that on 64-bit, they're now called RAX and RBX, and basically the same naming convention with an R in front. What is important about those registers is that originally they had a purpose assigned. So EAX used to be the accumulator, EBX used to be the base, ECX used to be the counter, EDX used to be the data register, and we have the source index and the destination index, and the base pointer and stack pointer. I said they used to have these purposes attached to them. In reality, they can be used in wildly different ways. This is where it gets a little complicated. So in reality, what the purpose of a register is decided by different entities. Some registers, in the context of certain instructions, have hardwired purposes. Like some instructions on the Intel architecture in a hardwired way rely on certain registers to function a certain way. I'll just leave that sitting here. Then the next thing that might assign certain purposes to register is the processor ABI, or essentially the compiler that implements function interfaces. The compiler in that case might decide that, for example, EAX is our return register. If a function ends with a return 1 or with a return 0, this return value would land in the EAX register. That's not defined by the CPU though. That is a compiler convention. like the ABI, the application binary interface, defines that EAX in at least in 32-bit Windows applications will hold the return value from a certain application. I kid you not. If you dig deep enough in the compiler, you can change that. I tried to do that once in GCC just for fun. I did not manage because GCC is crazy complicated and I didn't have the time to put in to dig down deeper. But I'm very convinced that if you try hard enough, you can teach GCC to use a different register as a return register than EAX. Anyway, that's just as a note on the side. So the purpose of these registers can be hardwired in the CPU, but not usually. It isn't usually. This is most confusing in the case of the base pointer and the stack pointer. We'll be talking about these in a bit in more detail. They basically manage our function stack. And what's so confusing about these is that they were designed to manage the function stack. They are usually used to manage the function stack, but modern optimization can cause these registers to be used for different purposes. And then they do not, by default, manage the function stack. Yeah, it's a little confusing. And that's especially true for the base pointer. But in this class, we will not be talking about optimization very much. Then the reason why I have this 32-bit slide in here is because I had this beautiful 32-bit graphic. Registers and the general purpose registers can be addressed in different ways. They can be used as like in the full 32-bit or in the full 64-bit, but they can also be used in parts. That means, for example, if we have a 1-byte value, like say we have a character is usually 1 byte big, right? And that character would not take up 32 bits. Like if you want to address a character in a register, we only need the bottom 8-bit that represent our character. And if we want to address that, like say, for example, we have a character stored in the EAX register, then we want to address AL. AL addresses the bottom 8-bit of the register. Yeah, just watching out that I don't tell you anything wrong. The mode of referring to registers in different size conventions are depicted in this beautiful pea green graphic, where you see that the 32-bit axis for EAX is EAX. This describes the full 32-bit in the register. If we only want the bottom 16-bit, is it the bottom? Yeah, I think it's the bottom. So the bottom 16-bit would be referred to as AX. The bottom 8-bit would be referred to as AL, and the upper 8-bit of the bottom 16-bit would be referred to as AH. I just see that the graphic looks a little confusing. I'll gloss over that. Anyhow, so the access modes I've just been talking about apply to all of the general purpose registers. So you can perform 16-bit access on AX and BX and CX and DX and so on and so forth, and 8-bit access on AH and AL and BH and BL and CH and CL and so on and so forth. This is important for us because sometimes this matters when we read the assembly in front of us to be able to figure out like what data types or like what data sizes we're looking at. And that might come in handy on occasion. Now, enough of history. How does it look like today? On a 64-bit system, we have the same registers, except that we have more of them. So on 64-bit, again, you don't see EAX and EBX, you see RAX and RBX and RCX and RDX, etc., etc. So there's the R in front. But then we also have another, a new set of 8 more general purpose registers, and they're numbered. So you have R8, R9, R10, R11, 12, 13, 14, 15. Altogether, that makes 16 general purpose registers. You can imagine if we just doubled our general purpose registers, that the whole thing is a lot more, like assembly is a lot more agile. Like there's a lot more things that we can do with registers. You might remember in the beginning I told you that registers are fast, 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 and stack is just fast, fast. In a sense, on 64-bit as opposed to 32-bit, what we see is a lot more register interaction, and compilers, especially when used with optimization settings, are trying to limit stack interactions. To limit stack interactions, they make heavy use of the general purpose registers. Again, the binaries we're going to be looking at here are not optimized. So in a bit, when we load the first exercise binary into disassembler, you will still see a lot of stack interaction. That's just up front. Then access modes work in a similar fashion as on 32-bit. So instead of RAX, we can reference EAX, AX, AL, and AH. And the same goes for the higher index general purpose register. So here the example shows R10, then to access the 32-bit portion, like the lower 32-bit of R10, you would say R10D. The D in this case stands for D word. By the way, the data sizes we're talking about are generally true whenever you see a D, a W, or a B. B stands for byte, W stands for word, D stands for D word, and 64-bit values would be called a quad word. Again, historical reasons. From time when processors were 16-bit based. All right, so now you understand the general purpose registers perfectly well, I know. And just to have mentioned, there is a whole stash of other registers, especially on 64-bit processors or on modern processors. We have extensions that are called SSE or AVX and so on and so forth. And with these extensions, the CPU manufacturers introduced new registers that you might spot in this assembly. In my experience, though, they are not very common. If you want to see funky disassembly, look at some cryptographic code, like disassemble a library that offers cryptographic functionality, and you will see all the most exotic registers and all the most exotic instructions in there. It's kind of hilarious. But honestly, I have no idea how to properly reverse engineer those, just because they're kind of rare. And naturally, we will not be covering those in this class either. Then, I mentioned before that the instruction pointer is like the one most important register we have in our system. Why is that so? You saw in that screenshot from the debugger that the instruction pointer is pointing to the next instruction that's going to be executed. That means implicitly that this register controls execution. A short excursion into security, if an attacker manages to gain control over the instruction pointer, like for example through a buffer overflow exploit or use of the free, or like how all those beautiful classes are called, like if any one or another way an attacker manages to load their own value or their defined value into the instruction pointer, they can divert the execution. The CPU, I can't say it doesn't care. Like the CPU does care what is executed and whatnot, but if the attacker is tricky enough, then the CPU doesn't know which instruction comes after which. So if the instruction pointer is tweaked, then the CPU will just happily execute whatever code the pointer points to. That's what I'm trying to say. We'll see in a bit when we talk about stack frames about like an example of how the instruction pointer is modified throughout execution. You can imagine that if you execute an application that has different functions, then you have one function calling the next function, calling the next function, that the instruction pointer needs to jump quite a lot. That is curiously exactly what the call instruction or what the jump instruction does. If you see a jump to a certain address, exactly what happens is that this address is loaded into the instruction pointer, and then the instruction pointer knows to keep on executing at a different space, like at a different location inside the binary. Yeah, it sounds like a simple concept, but in reality, like when you go reverse engineering a binary, it's not always that easy to figure out where execution will continue from one spot to another. Right. Yeah, again, we'll be talking about stacks and instruction pointers and stack frames in a bit. The flags and E-flags and R-flags. Someone in the chat asked whether we were going to talk about the status flags a bit more, and now we are. Personally, and other people might disagree, personally, I don't think that the status register is a good topic for beginners to dive in deep. What is the status register? So respectively 16, 32, 64 bits wide, depending on the architecture you're on. You have a set of flags that control execution. We will look at this a little bit later when we look at conditional jumps. Like in general, conditional instructions perform action based on certain conditions, and those conditions usually are based on the status of the CPU, which is indicated by the status register. There, for example, we see the bit number 6, which is the 0 flag. Bit number 6. I would have to look up whether it is actually bit number 6. Anyway, we'll see that in the debugger once we start debugging. The 0 flag is set if an operation resulted in 0. Like, for example, if we look at the compare instruction, we'll be looking at compare instructions in a bit too. Compare works in a way that it subtracts operand number 2 from operand number 1. So compare essentially is a subtraction where the two values, like it calculates the difference between the two values. Then if there is a difference, the 0 flag is not set because the result wasn't 0. If there is no difference, if the values are the same, the subtraction results in 0, and then the 0 flag is set. And then confusingly, there's jump instructions which check the 0 flag, which jump if 0, for example, the JC instruction performs a jump to the, it'll be easier to explain if we see a graph. So like jump if 0 jumps to a certain address if the 0 flag is set. It will not jump to that address and just continue execution in a straight fashion if the flag is not set. Then essentially what we see if the compare instruction delivers the result of 0 because the values were the same, the 0 flag is set, and the jump instruction will be taken to the indicated destination address because the compare was 0. The reason why I don't like to go into details about the status register with beginners is that you can just see it is a rather confusing, um, it's a rather confusing concept. But the way if I ever go silent in this training is because I'm trying to figure out how to explain something in a better way that it makes sense. In a bit, we're going to look at the graph representation of a binary in a disassembler. And you will understand a bit better about why the flags register, I believe, is not the most important thing to understand in the beginning. It's because the logic of the code flow often explains itself, and we don't usually have to look at the details of the e-flags. The e-flags register is important if we want to, like often when reverse engineering, you land in a function that's very important and you look at a certain snippet of assembly code that is very important to analyze in detail. And then it is good to keep track of the different flags in the status register. What other flags do we have in there? There is a carry flag, for example, if we have a carryover in an arithmetic calculation in the assembly. So if computer science introduction first semester, if we perform gosh, I need assembly to explain this, I'm sorry. Overflow, the overflow bit is set if an arithmetic operation on the CPU results in an overflow. And so on and so forth. Signed flag is set if we have a signed operation. Yeah, you see, I don't really like the e-flags register very much. Something that's interesting about it is that on 64-bit chips, it is 64 bits wide, but the upper 32-bit aren't actually currently used. This much about that. We'll get back to the e-flags register later on when we look at actual disassembly, where the tricky part there is if you're not in a debugger, like if you perform, if you statically reverse engineer something or you're just reading the assembly, you do not see the e-flags register. The screenshot that we saw before was from a debugger. When we're debugging, we see what's going on in the status bits. But when we just look at the disassembly, we don't actually see the e-flags. So then we have to think about what exactly is going on in our flags as we go reading the assembly. Moving on. Now, we're actually gonna go and do some reverse engineering. Beautiful. Just quickly looking at the chat. Yeah, Granless says that how assembly works and does math with the CPU is pretty deep in the woods, to be honest. It is. That is so true. Good. Example. We're gonna look at our first stash of assembly. Let me take a quick sip of coffee. Okay. If you've never actually read assembly, then there's a lot of Chinese in front of you right now. This snippet really doesn't do very much, and it doesn't show us very much about what it actually wants to do because we lack the context of what else is going on in this function. But what you see on the screen is basically string parsing. Where to start? So if you write C code and you define a string and an integer and a char, like a character variable, for you as a developer, there is a big difference, right? Integer is numeric and a string is lots of characters terminated by a null pointer, by a null byte. But big surprise for the CPU. None of these differentiations matter very much. So like whether we have a string buffer or whether we have an array full of integers or like an array full of, I don't know, pointers, for the CPU, this is all just data. And in assembly, we have several methods of parsing that data, like for example, of stepping through a string and operating on each different character. But in the assembly, you don't actually see the data type. What matters for the assembler or like for the CPU is the size that we're looking at. Like whether we have a byte pointer or a D word pointer or a word pointer or a quad word pointer, and how much data we load into a register or how much data our instruction actually operates on. This is all stepping a bit ahead, but stay with me. So what we see when we look at this stack of instruction is a couple move instructions, a couple add instructions, and a jump instructions, a jump instruction. Where do we start? Technically, I haven't shown you the slide yet that shows us the 20 to 30 instructions that we need to understand. So I totally understand if you look at the move instruction now and don't exactly know what it is. Stay with me there. Like the move is all the instructions on the screen are very simple. So move moves a value from a source to a destination. In the first case here, the source is a pointer, like a spot in memory that's pointed to. Let's put it like that. And the destination is EAX. That's the 32-bit part of the RAX register. If you look at that instruction, we have a D word pointer that loads a value into EAX. That tells us that we're loading a 32-bit value. Logically, you can't load a 64-bit value into EAX. Then RBP minus 24 is a location. RBP is one of the registers that I just introduced. Minus 24 is a offset, like RBP points to a certain spot in memory. Usually that's the stack. In this case, let me tell you, in this case, it is the stack. And minus 24 identifies a specific location on the stack. We'll get to the stack in a short time. If you remember that screenshot I showed you from the debugger, the stack, like this little box in the bottom, where you see this stack of values, RBP points to one of those values. With minus 24, we offset into like a different region of the stack where we can fetch a value, in our case, a 32-bit value. So we load a 32-bit value into EAX from the stack. By the way, these edgy brackets here mean that we resolve a pointer. That's a funny thing to explain. So if you imagine you're in a C program and you have a character pointer, like an array of characters, then the character pointer itself is a value, right? It is an address. And if you dereference the pointer, you get to the value that the pointer is pointing to. That is the same way the CPU sees a pointer. A pointer is an address, and if we dereference that pointer, we get to the actual location it is pointing to. That concept sounds simple. I see in the past with students that it's sometimes difficult to wrap your head around, like the difference between an address and the value that's located at that address. We're going to be talking about that a lot more in the future, don't worry. Okay, but what happens here, again, we load the 32-bit value from the stack. Then we take that 32-bit value and load it into RDX with a sign extension. This tells us that the value that we loaded was a signed value. If you remember from C development, you might have signed or unsigned integers, or signed or unsigned data types. And in this case, we just learned that our value was signed. So now we have a signed 64-bit value in RDX. If that makes sense. The numeric value is still the same. The numeric value is the same, but the width of the value has increased. That's a stupid way to put it too. Don't think about it too much. We load the 30-bit value from the stack, which eventually ends up in RDX. Then we do the same thing with the 64-bit value from the stack. So we load from this location, we load a quad word into REX. All right, so after this operation, we have a value here and we have another value in REX. We add those two. As you can imagine, add accepts two operands and adds them both and aggregates the value in the first operand. What does it tell us? We loaded two values from the stack and we added them, so the result is stored in REX. REX then, in the next instruction, is resolved. You can see reading assembly is very tedious, and actually what we want to get at with this whole stash of assembly up here is the compare instruction down here. So stay with me for a minute. We load two values from the stack, we add them together, and then we resolve REX as if it were a pointer and load a byte value into EAX. What does that mean? Essentially what that means, or what that suggests, is that one of the values we loaded from the stack was a pointer, and another value that we loaded from the stack was an offset. Then we're adding offset plus value, which points into a certain location. There is a bit missing in this assembly piece. What essentially happens is that we load a string, like we load the address of a string, and then we add an offset into that string. How that looks like is that that is a very common pattern that you see in string parsing. And string parsing is something that happens a lot in modern day binaries. For example, you're trying to calculate the length of a string. The most simple way to calculate the length is you take a pointer that points to the first character in the string, and then you advance the pointer byte by byte until you find a null byte, and you count as you go along. So then you would have a variable which is counted like +1 at each hop that you do through that string. Anyway, that's a little excursion. Let's get back to our assembly stack, assembly printout here. Again, we load a pointer, we add an offset. We're pointing into a string. And in this instruction is what we do is we load a byte from where our pointer is pointing to. This will be a character. That's something you can't deduct from this little piece of assembly, but just believe me, I copied these out of one of the exercise binaries that we'll be looking at. So this stash of assembly is real. We load this byte into EAX, and here you see a new fancy instruction. It's called move CX. Move CX stands for zero extensions. So here we have sign extended, and here we have zero extended. Zero extended just means that we load a byte into EAX, and everything that's bigger than a byte, like a byte occupies the lower 8 bits of EAX, and the upper 32 minus 8 bits of EAX that are left are set to 0. So then the only thing that's present in EAX really is the one byte that we loaded from this address. All right, and then we go on to compare this byte with the number 95. What might that mean? At this point, I think it's a good time to introduce you to the concept of ASCII characters. Characters or text for the CPU is nothing but numbers too. Everything we look at is numbers. Remember, everything on the computer is zeros and ones. The question is just how we represent it. And characters for the CPU, again, it's just numbers too, and they're usually represented in one or another encoding form. So like characters in the most rudimentary form come encoded as ASCII characters. Now don't ask me what ASCII exactly stands for, but if you want to follow me and look up an ASCII table. So I went to Google and typed in ASCII table, and what the ASCII table tells me is which numeric representation a character has in the ASCII format. Beautiful. Now here's a table. Wait, what were I? No, give me my bigger table. This is not okay. Never mind, it's just this one. So on the screen, you see what's called the ASCII table. Again, ASCII is a form of encoding. We as humans, we read characters. The CPU wants a number. That number represents a character. So like if we would parse an ASCII string from an disassembled binary, the disassembler most likely shows us the actual text representation. And in our case here, if you look at this assembly stack, we have 95 here. Again, from this assembly, we wouldn't know that this is a character, but I'm telling you that this is a character because I specifically copied a string parsing piece of assembly. We have the character 95. Now, if we go to the ASCII table, again, was curious here. I don't remember which disassembler I used, but this 95 is a decimal number. Typically, what the disassembler shows us is the hexadecimal number. Anyhow, it's just a matter of representation. Like the hex, whether something is represented as hex or decimal doesn't really matter. It's still the same numeric value. And in this table, thankfully, we have a decimal column and a hexadecimal column and even an octa column, which we never quite need anyway. And if we look at the decimal value 95, we figure out it's an underscore. You see that in the tiny numeric thingy down here? You have the 95, which also means 5F in hex and 137 in octa, and then the character representation is an underscore. Woohoo! So What we're doing here is we load a character out of a string and we compare this character with the underscore character. Dum, dum, dum. So, if you want to make an educated guess, what we're doing here is we're parsing a string and looking for underscores. I'll give you a second to think about that. Again, we load a string like a pointer to a string from the stack. Should. We load a numeric value which is added to that pointer and dereference the result. So we have a string which consists of certain characters. We add an offset so that our pointer points to one character in that string. Ideally, this is executed in a loop, and we point to the first character, second character, third character, fourth character, and so on and so forth. And with each character that we find, we check whether it's an underscore. So load character, compare with 95, and then what? After the compare instruction, you see a jump instruction, and an add instruction, and another add instruction. Now this is where it's getting interesting. Here on the right side, I copied the documentation for the compare instruction. Something I mentioned before, compare just takes the first operand and subtracts the second operand, and based on the result, it sets the status flags in the eFlags register. And as I mentioned, if the result is 0, so if AL holds the value 95, then we subtract 95 from 95, and the result is 0. If the result is 0, we will set the 0 flag to 1. This is where the eFlags register comes in. Thankfully, though, and this is why I personally don't look at the eFlags register all that often, instruction naming, or like the way that jump instructions are named on Intel, already suggest kind of what the compare instruction wants to do. So after compare, we see a JNE that stands for jump not equal. That suggests we will take the jump to the location .L5 if the values are not equal. So if AL is not 95, if the character that we loaded is not an underscore, we jump here. Okay? In reverse, if AL is 94, we do not take this jump, and execution continues linearly, which means if the value is not 95, continue executions here. But continue execution doesn't stop here. So essentially, after this add, we jump on to this add and keep executing. These markers here, or specifically this one marker, is cosmetics. Cosmetics in the sense that it doesn't mean anything to the CPU. It is here for us to be able to read better of what's happening in assembly. This assembly, as far as I remember, I think I copied it out of the compiler explorer. This is not how IDA Pro displays addresses. So if we would disassemble this piece of code in IDA Pro, first of all, we would see hex values instead of decimal, and we would see an actual address here. And the address would be the same of this add instruction. Anyhow, we see that later. But what I wanted you to understand is that if this jump is taken, we execute this instruction and continue from here. If this jump is not taken, we continue linearly and execute this add and then the second add instruction. That means that if the jump is not taken, we do not ignore this one instruction. If the jump is not taken, we execute this add. If the jump is taken, we do not execute this add. This is the only difference. And essentially what happens, if you look at the second add instruction down here, we add 1 to a pointer, specifically to that one pointer that is referenced with RBP minus 24, which is the same pointer as the one up here. Now think about that for a second. We increment that pointer. Eventually, we'll loop back to this code, and once we reach this instruction again, we will have increased the pointer that is used for dereferencing down here. What does that tell us? That tells us that this value here, the RBP minus 32, is the string offset, like the string pointer. This is what points to the beginning of the string. This value here is the index that we're using for looping through the string and jumping from one character to the next. And as we go parsing the string, we increment this value by 1. So with each iteration, RBP minus 24 increases by 1 and eventually reaches, well, the end of the string until we hit the null character. All right, but what happens if we find the underscore? All right, if we have this if AL is 95, again, if we do not take the jump is not equal. Okay, if we find the underscore, if AL is 95, we land with this add instruction and increment a counter. So RBP minus 20 in our case here is the counter. Phew, that was a long process. So essentially, we walk through a string character by character. We compare each character with the underscore. If we find a character that equals the underscore, we increment a counter. End of the day, what we do here is we look for underscores in the string and we count how many of them are in there. Whew. Okay, and this isn't even all the code. So like you see that reading assembly is kind of like scratching your left ear with your right hand and like reaching over here. So yeah, it's yeah, that's just how assembly goes. Computers do not think like humans. Like our brains see things differently. For a computer, again, they evolved from zeros and ones, and in their logic, things need to be represented in a way where they can consume a flow bit by bit by bit. Okay, this much about reading individual instructions. I see time for today is almost up and we're almost at the memory part. At this point, let me do a quick recap of what we did today. I promise you on Thursday, we will finish with whatever is left from the slides, and we will do a lot more practical things where you can get your own hands dirty. So today was really just a bigger part of theory. What we did today, we had a quick look of how a disassembler tool looks like, of how it produces the disassembly that we want to read. And we started understanding certain components of the CPU and how they help parsing instructions. Let me see if that was all. Yeah, registers. Talked a lot about registers. In reality, they're very, very important. If you look at the stack of assembly instructions, then Understanding the instructions is one part, and understanding what the instructions do to the set of registers is the other part. So yeah, that's why they're so important. On Thursday, we're gonna be looking a lot at stacks and heap as well. If I look ahead here. Yeah, so stay tuned. At this point, we have a few minutes left for questions, if you have any more of those. I'm super happy how my moderators are swinging the chat and answering the questions already. This is great. By the way, I'm the one speaking here, but BlackHoodie really is a collaboration among many different people, and I could not have put this training up and online and together without the help of many of our BlackHoodies. So yeah, this is really a collaboration. And at this point, I want to say a thank you, especially for my chat moderators who are eagerly chatting with you all and answering questions. That's so awesome. Also, putting BlackHoodie together is much more fun with when other people join in and do some part of the organization and the swinging the training. Yeah. Questions. Will we be having a look at exploitation? No, not in this class. Reverse engineering is a skill that you will definitely need if you want to write exploits. But it goes a little bit out of the topics that I wanted to cover here. What we did today and what we do with like going through the slides is really just scratching the tip of the iceberg. This is like the most abstract theory that we can do. The skills that you need for writing exploits include the reverse engineering part, but then also the how to go through the execution flow of binary and understand how binaries are supposed to function as opposed to how you can abuse the way they're supposed to function, if that makes sense. I just randomly pick questions out of here. What are your recommendations for someone wanting to be a malware analyst? So malware analysis involves reverse engineering, but in reality, there's so many other things you can do to analyze malware that do not require a disassembler, like static binary analysis. Tells you, like, is capable of telling you everything a binary does, more or less. But malware analysis itself involves a lot of dynamic analysis as well. And yeah, this is also something we don't really cover in this class. I personally think that if you want to be a good malware analyst, you should be able to reverse engineer malware. Reverse engineering regular software and reverse engineering malware is still a little different. Like malware usually tries to throw you off and usually tries to hide from the reverse engineer. And this is where it gets really tricky and really actually interesting when trying to reverse engineer malware. And I believe this is a very important skill to have if you work in that space. I know that there's many malware analysts though who do not actually reverse engineer binaries, and that is still fine too. Like you can figure out through other ways what a malicious binary tries to do. You might just not have the full picture and get all the details. And yeah, that's why I would say if you want to analyze malware, learn reverse engineering. It is a great skill to have. What else is in there? Do you have any tips on finding a good balance between going fast enough to get through a binary quickly and making sure you understand what's going on properly? That is a very good question. I guess it's a matter of personal choice. I am lazy, so I don't usually read instruction by instruction. What I usually do is trying to understand the bigger picture of a binary that's in front of me. That can be done by looking for strings in the binary or looking for API calls of interest. And that way, identifying pieces of code that are of interest and then reverse engineering in more detail there. Well, like, again, this one particular very interesting piece. Say you analyze ransomware and you want to know how exactly does it encrypt files, then you might want to find that encryption module or that encryption function and analyze in detail about how exactly does that. Usually, if you go reverse engineering a binary, you don't analyze the first byte and the second byte and the third byte and you work your way down to the last byte in the binary. That's not usually how the workflow goes. We talk a bit more about reverse engineering workflow when we analyze actual binaries, like when we go at the exercise binary, or later on when we look at the DLL I was promising. And yeah, the workflow for analyzing a binary is really depending on what it is you're looking at and what you're trying to achieve. Like, for example, if you want to write an exploit for a specific vulnerability that you found in the binary, then you might really want to understand that piece of code that contains the vulnerability to see like which input can trigger that vulnerability. But again, yeah, that's very, very specific for the use case that you're looking at. Um, yeah. Someone posted a link that helps learning exploit. For reverse engineering, same as for exploitation, there is hundreds of tutorials and blog posts and even books and videos and conference talks and all that stuff online. So like, if there's anything specific you want to learn that I'm not explaining in this class, I can recommend a website. It's called opensecuritytraining.info. They have a lot of trainings that go into different directions, including reverse engineering. Like they're actually really, really good and rather quite complete. Like lots of security and non-security trainings on there that people can dig into. And same as with exploit, like same as with reverse engineering, exploit development just requires a lot of practice. Like honestly, again, reading books is fun, but most importantly, get yourself an exercise, like get yourself a project and start working right away. And as you go working, you will find you have to answer some questions. And once you find the right questions, you can look it up in the book that you have or Google and see whether you can explain the theory behind the practical thing you're trying to do. All right, I'm afraid we're running out of time. And honestly, my workday is starting and I have to get some real stuff done. But yeah, I had a lot of fun today. Thanks you all for listening in, and I hope that I will figure out how to push this video to YouTube or like store it in one or another way. And yeah, I hope to see you all on Thursday. Excellent. And I'll stop streaming now if I find my way out of the streaming application. Yeah, thank you all for attending. Stop streaming now.